In this video, we will discuss some important topics that will most likely be on your unit test in AP Chemistry over acids and bases. You will need a calculator, and I would just ask that you put your phone away because this test tends to be the lowest test of the entire year in AP Chemistry, and so your focus needs to be at 100%. Okay, so strong acids versus weak acids. First of all, acids, they donate H+. And so strong acids, there's some that you could memorize. I would not worry about memorizing which ones are strong because you'll have them on the test. But for example, HCl is a strong acid, and what I know about that is that HCl dissociates 100% to produce H plus Cl minus. And so because of that, the concentration of HCl, because it'll dissociate 100%, it will equal the concentration of H plus. So typically with strong acids, no Ka will be given, okay, because there's no need, because all of the HCl goes to H plus. Now, with a weak acid, a common weak acid would be acetic acid, HC2H3O2, and that will react with water to produce H3O plus 1, which is the same thing as H plus, and it will also produce its conjugate base, which is acetate. And this is going to be a weak acid. And so because of that, it dissociates or reacts less than 5%. Now, we have to solve for the percent ionization if we want to know the exact percent, but it's going to be around 5%. It's not going to be a lot. Okay, and so I'm going to need a Ka to be given, and I'm going to use a Rice table. Okay. Now, strong versus weak bases, it's the same idea. Your strong bases, you could memorize what they are, and you're more than welcome to do that. But your strong bases are going to have hydroxide, and they're going to dissociate 100%. So the most common one we see, it seems, is sodium hydroxide. It will break apart to form sodium plus 1 and then hydroxide minus 1. And then your weak bases, we tend to see organic compounds here. And if you've taken organic chemistry, then some of these aren't so bad. But organic compounds that have this functional group or this group called an amine, and so we see something like a methylamine, which looks like this, and it will react with water, and it will produce hydroxide, so that's where we get hydroxide, and then it will produce the conjugate acid. Here it'd be NH3 plus 1, or you could have written it with an H out in front if you're not familiar with organic compounds. No big deal. Just put the H out in front, and so you get this. One thing that's important is to make sure you get the charge. So notice hydroxide is negative. This methylamine conjugate acid is positive. So this entire side is neutral. And if I look at the other side, it is neutral, so I feel like I've done it okay. Now, let's solve some multiple choice questions that I've chosen just because they're a little bit tricky. It says, what is the pH of a 0.015 molar solution of barium hydroxide? So that's going to be a strong base, but we've got to remember that if we have barium hydroxide, that's really BaOH2, and so if I have BaOH2, it'll dissociate 100% into barium ions plus 2 hydroxide ions. And so what I can do is I can say, well, if this is 0.15 molar, then hydroxide is 0.015 molar. If I take the negative log of, it's not 0.15 molar. That's a mistake. It's going to be double that through the mole bridge, so 0.30 molar. That's my mistake. POH equals the negative log of hydroxide, and we should be able to do this a little bit in our head, and we would say the negative log of 3 times 10 to the minus 2 is going to be about 1.5. I am going to plug that in just to verify. Negative log 3 times 10 to the minus 2, and I get 1.52. And so that's pOH, but oftentimes AP will just ask you about the pH, and so I take 14 minus 1.52, and when I do that, I get 12.48, so I think that would be the best answer here. Now, this is a good question because we want to know the pH of a solution. We've got 10 mils of 0.002 molar potassium hydroxide, but we're going to dilute it. And so when we do that, we've got to say, okay, well, I would normally just take the negative log of my hydroxide, that'd be pOH, 14 minus that would be pH, but the concentration is changing, so because I'm diluting and the volume is changing, I need to use my dilution formula. So the initial molarity was 0.002 molar, the initial volume was 10 milliliters. I am adding 10 milliliters, so the final volume will be 20 milliliters. Hopefully you can do this in your head, and that we are just going to divide this by 2, the concentration is 0.001, and so pOH equals negative log of hydroxide, and so negative log of 1 times 10 to the minus third equals pOH, and with that, the pOH should be 3, so the pH should be 14 minus 3 to give me 11. So I think B is the answer. Okay. So very good questions here. Now, let's talk about when to use Ka, Kb, and then how to get pKa and pKb. If I have an acid, it may seem obvious that I need to use Ka, but sometimes we have buffer solutions, and with that, we'll have an acid and its conjugate base sometimes, and so maybe it's not so clear. Well, you got to look at your reaction. If I have acetic acid, which is just a common acid that we see, and I've got this reaction that I'm writing out, plus C2H3O2 minus 1, I've got to say, okay, I produced hydroxide. Or not hydroxide, hydronium. That means I need to use Ka. I did not produce hydroxide. If I had a base, and I'm just going to write a random base, fluoride, plus HOH, that would give me HF plus hydroxide. Because here I got hydroxide, then I'd use Kb. So to use Kb, you need hydroxide as a product. To use Ka, you need H plus or H3O plus 1 as a product. Okay, very, very important. So to get pKa and pKb, we'll talk more about those later when we get to titration curves. But remember, if I put P in front of anything, that means minus log. So notice pH is equal to minus log of H plus. pOH is equal to minus log of hydroxide. So if I have pKa, that's just minus log of Ka. And if I have pKb, that's equal to minus log of Kb. Okay, so we use those kind of frequently. Other things that are going to be important that you'll probably know, but some of them maybe we don't use as much as others, is that pH plus pOH equals 14. And additionally, pKa plus pKb equals 14. And the reason why that is, both of these are true, is because H plus times hydroxide concentration equals 1 times 10 to the minus 14. This number, this is called Kw. Okay, and additionally, Ka times Kb equals 1 times 10 to the minus 14 as well. So a lot of these are interchangeable, and you might do the problem one way where you might see your teacher or someone else do it a different way. Okay, so just know that there are plenty of ways to do lots of problems that deal with pH, pOH, Ka, Kb, H plus, and OH minus. So let's look at some problems. Well, first, let's know what a Ka tells us. It's just an equilibrium constant. And it's specifically for acids. So a general acid equation would be HA plus HOH gives you A minus plus H3O plus. And with that, if I have a large K value, that means product favored. And so if I add an A there and make it Ka, it's still going to mean product favored. And so with acids, though, if I'm product favored, I'm producing a lot of hydroxide, so that would mean a strong acid. So this says what is the weakest acid? That means I want to look for the lowest Ka, and it looks like that would be HCN because it has the lowest Ka value. Okay, looking at this next problem, it says HA is a weak acid, and we're going to take some HA, and we're going to dissolve, what is the Ka? An aqueous solution of HA is prepared by dissolving 0.02 moles of HZ in sufficient distilled water to yield. Okay, so there's a typo here, but by the time that you get your paper, I will have fixed it. So this HZ needs to be HA. Okay, so we've got HA, and we take 0.02 moles of HA, and we dissolve it in distilled water. We get the pH, and it says what is the Ka of the acid. So think back to that citric acid lab that we did, where you created a certain molarity of citric acid, you measured the pH, and you were given the task of figuring out the Ka. So what a lot of people did is they set up a generic rice table where they said HA, the acid, plus water goes to A minus plus H3O plus 1. And we're taking 0.02 moles, and it's going in 1 liter, so the molarity is 0.02 to start out with. Minus x plus x plus x, x, 0.02 minus x. So our Ka expression is equal to A minus H3O plus 1 divided by HA. Always write your Ka expression because there will always be a point associated with that. That equals x squared divided by 0.02 minus x. But we're solving for Ka, so what I generally say is that, well, there must be a clue as to what x is. And what that clue is it's this pH. If I take 10 to the minus pH, that will give me just H plus. And since I have H plus or H3O plus in my reaction, and that represents X, that would be useful to me. So I'm going to take 10 to the minus 4.93. And let me plug that in, 10 to the minus 4.93. And that's going to give me 1.17 times 10 to the minus 5. Now, ask yourself this question. Do you need to use the 5% rule here? The answer is no, because we're not solving for x. We know what x is. It's this number. We only use the 5% rule when we are solving for x. So we'll take 1.17 times 10 to the minus 5. We will square it, and then we'll take 0.02 minus 1.17 times 10 to the minus 5. And I'm going to plug that into my calculator. Squared divided by 0.02 minus that. And I'm running out of room, but my Ka looks to be 6.91 times 10 to the minus 9. And since that is an answer, I feel pretty good about it. Now, one thing that gets a little bit tricky is sometimes you'll see a question like this, but it will give you a base, and they'll give you the pH. Well, remember, bases produce hydroxide. Okay, so I'm thinking back to a question that looks like this. If I had a reaction, let's say they give me the concentration of fluoride. Then if I gave you the pH, you got to get it to the POH and then turn it into hydroxide to get X, since that's what you have in your reaction. Okay, there was one on a quiz I gave like that, and it was on the second page of the quiz. Very good question. Okay, percent dissociation. A lot of people always overthink that, but what you want to know is that we've got HClO plus HOH. We're just going to set up a generic rice table and plug in what I know. A lot of these are going to look the same. We've got 0.015 molar of our acid, 0 minus X plus X plus X, 0.015 minus X, X, and X. So Ka is going to end up being H3O plus 1, ClO minus 1 divided by HClO, which equals X squared divided by 0.015 minus X. And we want to know the percent dissociation. Well, Ka here is 3 times 10 to the minus 8. Here we can use the 5% rule because we're solving for X, so I'll get rid of X. Multiply 3 times 10 to the minus 8 times the denominator, which is just cross multiplying, and I get that X squared equals 4.5 times 10 to the minus 10. I should be able to do this a little bit in my head, that X is going to be about, and I'll plug it in to know the exact number. It's going to be about a little over 2 times 10 to the minus 5. I'll get the exact decimal. And it's 2.12. But notice, here's why AP Chemistry is so hard. That's an answer. But that's not the percent dissociation, okay? What the percent dissociation is your X divided by initial, okay? And X represents how much actually broke apart. So we just want to know how much broke apart divided by the initial. So we're going to take 2.12 times 10 to the minus 5. We're going to divide that by 0.015. Times it by 100 to turn it into a percent. And let's see what we get. I get 0.14, which is a little bit low, but that's what my math tells me. So this must be a pretty weak acid. So this is a real answer, E. Okay. So what would you do with polyprotic acids? Polyprotic acids are acids with multiple H's that can be plucked off. But remember, the key idea with polyprotic acids is they give away one H at a time. So what you end up with, and we'll get into this with titration curves, is let's say I had H3PO4 and I titrated it. That's got 3 H's it can give away, so I'd get one equivalence point, a second equivalence point, and I'll mark those like that, and then even a third equivalence point. Okay, 3 equivalence points because I have 3 H's, and as I take off an H, it becomes increasingly more difficult. Now, when you see a question like this where it gives you H3PO4, Ka1, Ka2, Ka3, and you want to know the pH, all you're going to do is worry about the first one to pluck off. So H3PO4 plus HOH gives you H2PO4 minus 1 plus H3O plus 1. Set up a rice table. 2.50, or not 0, but X, 0 minus X plus X plus X, 2.5 minus X, X, and X. Ka equals H2PO4 minus 1, H3O plus 1, divided by H3PO4, which that Ka, this is for Ka1 right now, and that's going to be 7.5 times 10 to the minus third equals X squared divided by 2.5 minus X. We can use the 5% rule, and to speed things up, I'm going to solve for X, so you might need to pause the video to make sure you can solve for X. So 7.5 times 10 to the minus third times 2.5, and then 1 divided by 2. My X is 0.137. And it wants to know what the pH is. So notice, they give me something that is X, but that's not the pH. I've got to take the negative log. pH equals minus log of H plus or H3O plus. So pH equals the minus log of 1.37 times 10 to the minus 1. So that pH will be a little bit less than 1. And let me take the negative log of that. pH is going to be 0.863, which the closest is to C. Now, notice I did not pay attention to Ka2 or Ka3. They're going to be mathematically insignificant. If you want to do the math on that, that's fine, but you'll waste a whole bunch of time. So never pay attention to Ka2 or Ka3. Okay. Now, pH of salt with good justification. So, I'm going to focus on two main types of salts. I'm just going to get it out of the way. Acidic salts will have ammonium. Okay, that's the only one AP is going to show you. So just know that. So that would be like ammonium chloride, ammonium bromide. I'm not going to get into that because it's a little bit complicated, and I would not worry too much about that. But let's talk about other types of salts. So let's say we had sodium fluoride as a salt. I'm going to erase some of this to make some room for myself. Okay. Now, sodium fluoride, let's look at sodium chloride. Let's look at sodium acetate. And let's look at like potassium. Well, let's just look at these three and we'll talk about them. So what I want you to do is when you see this, you want to react it with water and just do a double replacement reaction. Okay. And we're going to get, where's my red? We're going to get sodium hydroxide, sodium hydroxide, sodium hydroxide. So that's one product on all of these. And then we're going to get hydrogen chloride, hydrogen fluoride, and hydrogen acetate. Okay, and then hopefully you know that sodium hydroxide is a strong base. And then hopefully you know HCl is a strong acid, HF is a weak acid, and acetic acid, HC2H3O2 is a weak acid. So here's what I know, and I would show your work kind of like this because it'll be very clear for your grader on the AP test. Strong base, I would say, dissociates 100%. That is what strong things do. So I can say that for sodium hydroxide. Okay, and I can also say that for HCl. Now, I can say that HF and HC2H3O2, they do not dissociate 100%. So let's say, I'm just going to use a number, and I'm just going to say, let's just say about 5%. Okay? What does that mean in this first example? If hydroxide dissociates 100% and your hydrogen and HCl dissociates 100%, you could think of it like you had 100 hydroxide molecules. How much acid is there to neutralize it? 100 H's from HCl. So I would say there's no leftover H or OH, H plus I should really say. So the solution is neutral. Okay. With this second example, sodium hydroxide and HF. Sodium hydroxide dissociates 100%. HF dissociates 5%. I've got 100 hydroxides, let's say. The amount of H's to neutralize that is only 5. So I have leftover hydroxide that is not neutralized. So the solution will be basic. Okay. And that is the same answer for this last one because I have strong base and weak acid. Okay, that is the type of justification you need on an FRQ. You don't want to just say something about how if two strong things are present, no one wins. Okay, that's not very good chemistry because that makes it seem like a battle. It's not necessarily like a battle. It's more about that there's leftover hydroxides versus not having leftover hydroxides. Okay, so just to make sure that we answer the question very clearly, this first one is going to be neutral. It's a neutral salt solution. These last two are going to be basic. Okay, now, how could I get the pH of something if I had specific numbers? Well, I've got a 0.15 molar solution of potassium fluoride, and so they give me the Ka for hydrofluoric acid. So what I want to do is I just want to set up a rice table. I've got Kf plus HOH, and I'm going to get potassium hydroxide plus I'm drawing a blank, potassium hydroxide plus HF. Okay, goodness, that took me a while. Now, here's what I can tell already. They want specific numbers, but I can already narrow down my choices. I have got a strong base and a weak acid. So because this is multiple choice, I know that it is going to be basic. My guess is it's going to be just slightly basic, so about C. E's probably not what I would pick. So here's a tip for you. Pick C and then prove it later if you're running out of time. Pick C, move on, you can come back to it. You just got to remember to come back to it. But I honestly have not made a key to this, so we're about to find out if it is C. But I know it's got to be C or E. E just seems a little bit high. Now, what I'm going to do is I'm going to say, okay, 0.15 molar. Water is X. 0, 0, minus X, plus X, 0.15 minus X, X, and X. So my K is equal to KOH, HF, divided by KF. And commonly, when we get to net ionic equations at the end of this, you'll see the potassium's not there. You'll see F minus 1 and hydroxide minus 1 because potassium will drop out when you get a net ionic equation because it's just a spectator ion. But anyway, I just drew it like this, but either would be fine. This is going to end up equaling x squared divided by 0.15 minus x. And I've purposefully not labeled K. K has got to be KB because we're producing hydroxide. So this is where a problem can get tricky. They give you Ka, but because we produced hydroxide, I always want something to start over here on my rice table. That's just where I'll be most successful at. So what I've got to say is Ka times Kb equals Kw. So my Ka here is 7 times 10 to the minus 4. Kb, that equals 1 times 10 to the minus 14. My math will be 1 times 10 to the minus 14 divided by 7 times 10 to the minus 4. So let me plug that in. And my Kb is 1.43 times 10 to the minus 11. I can use the 5% rule because I'm solving for x, so times 0.15, take the square root of that or take it to the 1/2 power, and x gives me 1.46 times 10, how many zeros is that, times 10 to the minus 6. So I want pH, so I'm going to take the negative log of 1.46 times 10 to the minus 6. I know that that is going to equal about 5 point something, a little bit more than 5.5, but minus log of this, 5.83. And notice that's an answer. But because X was hydroxide, this is POH. So I'm going to take 14 minus 5.83 and 14 minus 5.83, and I get 8.17. And I can take a sigh of relief because I did predict the right answer. So what I'm trying to show you is that because you'll have about 25 multiple choice questions, something in that ballpark, Sometimes you just got to work fast through some of them, and most of the time, I would say that you could probably predict what the answer is going to be, because with things being acidic and basic, sometimes you know if it's going to be basic, and that's only 2 of the answers here. Okay, so you really save yourself some time. Okay, let's talk about common ion effect and buffers. A common ion would be like having HF and sodium fluoride, which would be NaF. People get very confused because of the sodium, but just think about it as a spectator ion. It's really there, but in a net ionic equation, it would not show up. So, a buffer, we've got to talk about that. Most people can tell me that a buffer, it resists change in pH, and I think that that is very good to know. Most people can also tell me that if I give you a titration curve, people can say the equivalence point is at X, the half equivalence point, let's just call that Y, and in that range of the half equivalence point, we would call that the buffer region, and we would call it the buffer region because that region has a slope pretty close to 0, and so because our y-axis will be about pH, and this would be volume of base added for this specific titration, because this is acid getting titrated with the base, that this has got to be the buffer region because the pH is not really changing. Okay, and I agree with all of that. However, here's what I want to be able to do, is I want to be able to say, well, if I have HF, and it breaks apart to H plus F minus, you could write as a reaction. A good buffer contains a lot of HA, which is just your acid, which here with this example is HF, and A minus, which is its conjugate, the thing that has loss in H. It's going to contain a lot of that. And here's the reason why. That let's just say I have 5 molar HF and I have 5 molar F minus. That means they're in a 1-to-1 ratio, which would be ideal. If I add some acid, H plus increases. Let's put that in a different color. H plus increases. So I'm going to shift left. Well, in order to go left, I've got to have some fluoride around. So what happens is, if I shift left, F minus reacts with any added H plus, and there is no net gain of H plus because I've just reacted with it, so there's none left over, so the pH stays about the same. Okay, so that's why it's important to have a lot of the conjugate base, this guy. Okay, so that's one reason. Now, let's say I add hydroxide. Well, if I add hydroxide and H plus plus OH minus give you, and I should really use a yield sign instead of an equal sign, give you water, and so my H plus concentration decreases. That's going to cause my reaction to shift right because it's going to try to replenish the H plus. Well, if I'm shifting right, my reactant HF needs to be present because that is what's going to produce my products. Well, because I have so much HF at 5 molar, HF replenishes any lost H plus, and so my pH is equal to negative log of H plus. So because I'm just replenishing any H plus that I lost, my H plus in my pH calculation doesn't really change, and so that's how the pH doesn't change. Okay, so that's the understanding of buffers that you need to have in terms of what's happening and being able to explain it using words. Very hard concept, I will give you that, but AP is for sure going to put that on your AP test, and I know I have put that on your test. Okay, let's talk about the math. Now, the buffers, you can use a rice table, and that will give you the answer every time. Or you can use a little bit easier of a method, and it's called the Henderson-Hasselbalch equation. And this will be fun for me to spell because I probably ruined it, but that's what I'm going to call it. And that Henderson-Hasselbalch equation is saying that the pH is going to be equal to the pKa plus the log of your acid in your denominator. So anything with an H, that's going to be acid. And its conjugate, A minus, specifically the conjugate base, in the numerator. It does technically have another equation, and that would just be the base version of this. POH equals pKa, or not pKa, pKb, plus log of now base in the denominator, and then conjugate acid in the numerator. Okay, either is fine. Typically, though, we're going to use this first one, so I'm going to erase this bottom one. Okay, so let's look at an example problem. It wants to know the pH of a solution of ammonia dissolved in 0.05 molar ammonium chloride. Okay, so a couple ways to do this is I'm going to show you both ways. I think it's valuable, and if you want to fast forward through this problem, once I do one way, that is totally fine. We could say NH3 is going to be a base. It could react with water, and it could give you NH4 plus 1 plus hydroxide. And you've got 0.01. You've got X. You've got 0.05. And you've got 0, so we'll say minus X plus X plus X, 0.01 minus X, 0.05 plus X, and X, okay? And I'm going to make that a little bit smaller to give myself some room. So our K expression has got to be Kb. The reason why it's got to be Kb is we produced hydroxide. So Kb is equal to NH4 plus 1 times hydroxide divided by NH3. Okay, that Kb, which I'm just going to write out the number, is 1.8 times 10 to the minus 5 equals 0.05 plus X divided by 0.01 minus X. We can use the 5% rule. Get rid of plus X's and minus X's. And when I solve for X, I'm going to take 1.8 times 10 to the minus 5 times 0.01 and then divided by 0.05. And my X is 3.6 times 10 to the minus 6. So when I take the negative log of that, I'm going to plug that into my calculator. That's going to be POH because X was hydroxide. The POH of that is going to be about 5.5. And get 5.44. So the pH, 14 minus 5.44, is 8.56. Okay, so that's one way to do it. Perfect answer. We know what the answer is going to be. Now, here's where it gets a little tricky. What if, or it doesn't get tricky, it just gets different. What if you looked at this a different way? Okay, so I'm going to delete all this. And what if you looked at it and you said, well, why couldn't we just take NH4 plus 1 plus HOH? I'm just ignoring the chloride. It's just a spectator ion here. And water could be a base. And so we could produce NH3 plus H3O plus 1. Set up a rice table. And we could say 0.05 X, 0.01, 0 minus X plus X plus X, 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 and this is 0.01 plus X, 0.05 minus X, and K is going to be equal to NH3. Well, actually, I want to move it over here like I did previously. K is equal to NH3, H3O plus 1, NH4 plus 1, and that's going to be Ka. I know that because I'm producing hydroxide. So my Ka, to figure that out, I'll have to do some math, but my Ka is equal to 0.01 plus X times X divided by 0.05 minus X. And I can get rid of minus X and plus X. And Ka times Kb equals Kw. Kw is 1 times 10 to the minus 14. Kb is given, and that is 1.8 times 10 to the minus 5. So if I take 1 times 10 to the minus 14 divided by 1.8 times 10, 1 e to the minus 14 divided by 1.8 e to the minus 5, my Ka is 5.56 times 10 to the minus 10. So times that by 0.05, then divide by 0.01, and my X equals 2.78 times 10 to the minus 9. If I take the negative log of that, my pH will be the answer, and I get 8.56. Okay, so that's, you could use the Rice table with Ka or Kb. Now, be patient with me here if you're watching through this problem. I could do this another way. This is probably how I would actually do it. This is a buffer. I know it's a buffer because I have a common ion. Well, let's just say buffer is equal pH equals pKa plus log of the acid, the thing with more H's. So that would be ammonium, so 0.05. And in the numerator, it'll be the base or the conjugate base, 0.01. pKa is negative log of Ka, so this is minus log of 1, or we had, what was the Ka? We had just had the Ka. It was 5.56 times 10 to the minus 10. So I'm going to write this a little bit smaller, 5.56 times 10 to the minus 10, and I apologize that this is a little bit sloppy. Okay, and if I plug that into my calculator, minus log 5.56 times 10 to the minus 10 plus log of 0.01 divided by 0.05, my pH equals 8.56. So just showing you that Henderson-Hasselbalch does work. Now, I could even do it a different way. It's all the same math. It's just there's a lot of ways to do this. I could say POH equals PKB plus log of base in the denominator because we're using PKB. So that would be 0.01. And then conjugate acid in the numerator. And my PKB is minus log of my KB. So POH equals minus log. My KB is 1.8 times 10 to the minus 5. I plug that into my calculator, and I'm just going to prove it to myself. And my POH equals 5.44, leaving my pH to be 14 minus that, which will be 8.56. This question kind of explains why acids and bases is so difficult for a lot of students, is because students want to generally find a way to memorize, and I don't know that that's necessarily bad, but you've got to still be able to problem solve. And so I just problem solved this 4 ways to solve this, basically, each of them equivalent. Okay, so don't get in the habit of just memorizing. Problem solve at least part way through it, okay? And that's going to do a lot for you. Okay, so when I get to this next question, it says how many moles of this must be added to 1 liter of 0.1 molar HCOOH, and since this has an extra H, although it's kind of weird that AP put it on the end, but anyway, this must be my acid. This must be the conjugate base to prepare a buffer with a solution of 3.4. Those of you that are still in Algebra 2 probably has not gotten to logs or maybe has just started, but we're going to use Henderson-Hasselbalch. pH equals pKa plus log of HA in the denominator and your conjugate base in your numerator. So let's plug in some things here. The acid concentration is 0.100 molar. We are trying to solve for the conjugate base concentration. And since we have a 1 liter solution, when we solve for that molarity, that will also be the moles, because remember, molarity is equal to moles when the volume is 1. pKa here is just negative log of Ka, so minus log of 2 times 10 to the minus 4. And then pH, they tell us we want it to be 3.4. So negative log of 2 times 10 to the minus 4 is 3.70. That equals 3.4 plus log of question mark divided by 0.1. So I get negative 0.3 equals log of question mark divided by 0.1. If you remember when we did natural log, let's just say natural log of x equals 65, we would take e to the 65th power to get x. That was natural log. We are just using logs, which is slightly different. Logs are base 10. So if we had log of x equals 65, we would take 10 to the 65th power equals x. So what you need to do here, I'm going to make this a little bit smaller, is we need to end up taking 10 to the minus 0.3 equals question mark divided by 0.1. 10 to the negative 0.3 is 0.501, and that equals question mark divided by 0.1. Times that by 0.1, and I get 0.05. And so B looks to be the answer. Okay, hard question, especially if you haven't done logs in Algebra 2 yet. Okay, this is a really good question. This is getting into what we talked about at the beginning about how buffers work. I'd understand this question. It says when a small amount of 12 molar HNO3 is added to a buffer solution. Right now when I see buffer, I'm saying the pH barely changes. Okay, if it's a buffer solution, we've got this and we've got this. This has an extra H, so this is my acid. This is my conjugate base. The pH of the buffer solution changes from 10.64 to 10.62. We did add a strong acid, so it should change a little bit, but since it's buffer, it's not going to change a lot. And since we're adding an acid, it should go down. Which of the following equations represents a reaction that accounts for the fact that pH does not change significantly? So we've got CH3NH3 plus 1, and that breaks apart into CH3NH2 plus H plus. And so what's happening is we have added H plus through my acid. But the pH barely changed, so whatever I added must have reacted with something. Well, I've got my conjugate base right here. And so what I need to do is just find the reaction that shows that. So I think that that's going to be A. And so that looks to be the final answer. And because whatever H plus I added ends up being reacted, there's not a whole bunch of H plus that's actually staying around that I added. So the pH is going to stay relatively the same. Okay, titration curves. A couple things about titration curves is if I have something like this, I know I started out with acid. Okay, But I can't tell if it was strong acid or weak acid unless I look at the equivalence point pH, because strong acids can have higher pHs if you just have a very dilute sample. So if this pH equals 9 and this pH equals 7, this must have been a strong acid. This must have been a weak acid, because when I mix a strong acid with a strong base, we know that at the equivalence point, the pH is going to be 7. But if I mix a weak acid with a strong base, it's going to be slightly basic at the equivalence point. Okay, so that is important. Now, looking at this graph right here, Z, that represents equivalence point. And at the equivalence point, the moles of acid that you started with are going to equal the moles of base that you have added. And a helpful equation to be able to do that for you is MaVa equals MbVb. Okay. And at the equivalence point, this is where your color changes if you have set up your titration correctly. And it looks like this took 60 milliliters to reach the equivalence point. Okay, so kind of a long titration. So X then represents what? Well, that's at 30. So X must be the half equivalence point. And at the half equivalence point, that means half of your acid has reacted. It has reacted and been converted to the conjugate version, which is the conjugate base, which is A minus. That is why it's very important to know that at the half equivalence point, pH equals pKa. Because if I have the Henderson-Hasselbalch equation, pH equals pKa plus log of A minus divided by HA, well, if we're at the half equivalence point, these guys, let's say they're both 5 molar. That fraction is just 1. Plug into your calculator right now. The log of 1 is 0. So this is just saying that you're using the Henderson-Hasselbalch equation. This whole region right here, that would be like your buffer region, anything that's relatively flat. Okay, and so you could use the Henderson-Hasselbalch equation. Here's what I would make sure you know as well, is that here what you have is a lot of HA, your acid. Specifically at X, HA and A minus, your conjugate, are equal. From Y to Z, you have a lot of A minus now. At Z, moles of acid equal moles of base. And anything after Z, that means you're past your equivalence point, which is not something that we generally do in lab. You just have leftover hydroxide that can't react because all the acid has reacted, and that's why the pH starts to shoot up really a whole bunch. Okay, so I would know that definitely. And we could have a base titration. So maybe something that looks like this. Our equivalence point would be the midpoint where it goes vertical, so about 15. So my half equivalence point would be about here, which would be about 7.5 milliliters of acid added. Judging on how I drew this, the pH at the equivalence point is 7, so this must have been a strong base with strong acid. So what do I have a lot of initially? Before I get to the halfway point, I have a lot of base. Between here and there, I have a lot of conjugate acid. And after that point, I have a lot of leftover strong base, or not strong base, strong acid that never reacted, okay? What would a titration curve like this look like? Oftentimes, AP will put two titration curves on the same graph, and so here's what I know is, and I'm going to draw them in color. Let's say titration curve number 1 is blue, and let's say titration curve number 2 is red, and I'm going to draw them. They're basically overlapped, but I'm trying to still show some blue. Okay. The equivalence point for red would be the midpoint of where it's vertical, so that would be about there, whatever that pH is. The equivalence point of blue would be the midpoint of where it's vertical, but it's only vertical for this section, so that would be about there. And that pH would be about here. So what a lot of people would say is that acid 2, which is red, is the stronger acid because it has a lower pH. We'll talk about why that is true in this specific case, but a better reason to mention is to mention the pH at the equivalence point. Because the pH, let's just call that 7, and this one 9, because the pH at the equivalence point is lower, it must have been a stronger acid. That's what I would say. Now, what is true about these acids? They take the same amount of base. The volume, let's just say, is 25 milliliters. And so because of that, in this case, if I did MAVA equals MBVB, volume of base, let's just say, is 25 milliliters. Let's just call it 0.1 molar for each of them. I'm just going to add that as 0.1 molar. And let's say I used 25 milliliters of acid for each of them. Then VA is 25 milliliters. So when you solve for MA for both of them, you get 0.1 molar. So how is it possible that they have the same concentration but a different pH? Well, because they're different acids. Some acids give away more H's than others, and so that's what we're seeing here. Acid number 2 is a stronger acid. And what does that mean then? Its Ka is larger, and it gives away, which means that it gives away more H's. Or I should really say a higher percent of its H's compared to 2. Okay. So what would we see here? We've got an amino acid, aspartic acid, and it's got a reaction. It gives us a pKa of 5 or of 3.65. And if we're at a pH of 5, how does the concentration between the two forms compare? So I kind of think about this as a titration curve. At the halfway point, that's where pH equals pKa. So I'm just going to give a number, 30 milliliters, which means right about here, it's going to be about 60 milliliters. And they tell us that this pH at the halfway point, that's what the pKa is, 3.65. I don't know what that is, and I don't know that I'm going to need to solve that out. But what I can add to this is I can say, well, before I get to the halfway point, I've got a lot of acid, or HA. Once I get past that halfway point, I've got a lot of its conjugate. Because the pH that we're at right now is 5, we are past the halfway point. So we're probably somewhere in this region. And so what that means is that the conjugate is present more than the actual acid. So I think the answer there would be C. Okay, last thing is net ionic equations. I'm going to go through this pretty quickly. We've got nitric acid, that's HNO3, plus potassium hydroxide. And in a double replacement reaction, we're going to get liquid water. These guys are both aqueous, plus KNO3, which is aqueous. We're going to break apart aqueous things, and so HNO3, that's a strong acid. So since it's a strong acid, it dissociates 100%, so it is best represented as H plus NO3 minus 1 plus K plus OH minus gives us HOH liquid. We're not going to break that apart. Plus K plus NO3 minus 1. Now I can cross out the nitrates, the potassiums. So what I'm left with is, oh, I deleted it and I meant to copy it. This guy plus hydroxide gives us HOH liquid. That is what you should expect to see when you mix a strong acid and a strong base, just forming water. The difference is when you get, and this is what AP tends to ask, is when you get a weak acid like acetic acid. Since it's a weak acid, we can still react it with sodium hydroxide. We get NaC2H3O2, sodium acetate, plus we still get water, HOH. And because this is a weak acid, it's best represented together. The reason why is weak acids dissociate at around 5% or less. So it would be incorrect to have this broken apart when it's staying together about 95% of the time. Plus sodium plus 1 plus hydroxide plus Na plus 1 plus C2H3O2 minus 1. This is liquid, so plus HOH. The only thing that you should expect to cancel in a weak acid strong base mixture or like a titration would be just the cation like sodium or potassium. And so what I'm going to end up getting is this same reaction, but all I need to do is just get rid of my sodiums and I get something, and my HOH is ugly. I get HOH liquid. Okay, so I am done with my review. This test will be a tough test. I don't think anyone's going to walk away from it saying, wow, that was the easiest thing I've ever done in AP Chemistry. But as long as you put in the work and you're more focused on problem solving than just memorizing, and you do all the resources you have available to you, you should be able to make it through that test.